Hello. In this video we are going to discuss classification metrics, and I would like to discuss some business tasks as well, and not only giving you formulas of some classification metrics like accuracy or precision or Rock-Oak curve, but I'm also going to discuss the advantages of and disadvantages of these metrics in real-world projects, and this will culminate in our practical part where we will take a look at a real-world task, and we'll see that actually choosing your metric very carefully is going to be a very important question. So typically you start a data science project, and one of the first things to do actually before training your models is of course to collect a data set, but also to agree upon some metric. So what actually means that your model is good, performs well? You need to agree upon that with your boss, with maybe your clients, with other data scientists in your group, and these questions really arise in the beginning of any project, and therefore they are sometimes really crucial. Okay, so we'll start with the simplest case of a binary classification task. And let's just start with a simple confusion matrix. So we've got some predictions of our algorithm, either 0 or 1, and the reality, the true labels, are also either 0 or 1. Let's just start with this very simple case, and we'll see that even in this case it's not everything is so obvious. Okay, so I'll write our predictions here and our true labels here. This will be 0 and 1, both for prediction and true labels. Obviously this gives us 4 variants, and we'll call this one true positive. Okay, so not I'm calling this, but this is typically called a true positive. Then a true negative is going to be depicting, correctly identifying a negative object. And there are two possible errors. One is called false positive. So if our object is actually negative, so instances depicted with label 1, I'll call these positive. And with 0, these are, though 0 is not a negative value, but still a 0 label is also called a negative label, negative example. Okay, and so if our model predicts that object is positive, but actually it's negative, we'll call this error a false positive, and conversely, we'll have a false negative. If our model predicts that this is going to be a negative, but actually it's a positive, this is going to be false negative. Okay, and so the simplest possible metric of the success of your algorithm is going to be accuracy. Accuracy is a very intuitive thing, so all your clients, all your bosses are going to understand it, all managers. So just a share of correct answers of your algorithm. So in terms of these 4 true positive negatives and false positive false negatives, a formula for accuracy is going to be really simple. True positive plus true negative. So all cases when the algorithm is correct, divided over the sum of all these 4 alternatives. So accuracy is a really very simple metric, and therefore it has lots of disadvantages. And the most obvious one is that it doesn't distinguish false positive and false negative. So you see here, even in this formula, false positive and false negative come with just the very same coefficient, and accuracy doesn't distinguish between these. But let's take a look at this. Maybe false positives and false negatives shall be treated differently in each case. Let's just think about the very same confusion metrics, but for some applications. Let's say classical maybe one of the first historical successful implementations of machine learning models is for spam detection. Okay, I'll be writing several confusion matrices, but for different tasks. Let's just take a look at three ones. And the first is going to be spam detection. Okay, so just the same, we'll have true labels and our predictions. So true label in the left column is going to be a truly spam letter and non-spam. And in rows we'll have predictions. So the first row will be predicted spam, and the second row is going to be predicted non-spam, normal letter. Okay, and let's just think of the importance of false positives and false negatives. Okay, so how do we interpret false positive? It's a normal letter, but the algorithm says that it's spam. And false negative is interpreted as a spam, but our algorithm misses it and treats it as a non-spam. Okay, just pause the video for a couple of seconds and think of what is going to be a worse mistake, false positive or false negative here. Okay, and so obviously here false positive is much worse, right? So if the algorithm predicts spam for a normal letter, then it's going to remove it from your inbox, and it's really very serious. So this might be your boss informing you that you're going to do a very serious report tomorrow morning, but you got it into spam and you haven't seen it. Okay, lots of problems. On the contrary, false negatives are going to be some spam messages that you see in your inbox. It's also not really very nice that you see spam in your inbox, but still not as serious as false positives here. Okay, one picture about these types of these errors. Okay, no better picture than this one. So false positive is to say that you're pregnant to a man. Okay, and false negative, do I need to comment it? You see, you're not pregnant. Okay, so the best picture ever illustrating this. And let's take a look at some more applications. So from the first example, we might think that false positive is more serious here. So just in this case, false positive was a much worse mistake than a false negative. Okay, let's take another one. Let's think of some algorithm predicting cancer. Okay, just to put it really simply without any details, an algorithm just says whether there is cancer or not, whether a client has a cancer, a patient has some form of cancer or not. Okay, so these will be true labels, and these again will be predictions, 1, 0, 1, 0, and again false positive and false negative. And in this case, definitely false negative is going to be much worse. So false negative will be interpreted as skipping the ill patient. So there is cancer, but our algorithm doesn't detect it. So this is going to be much worse. And you see, in this application, we'll take care of false negatives. Okay, one more example of a really very trivial prototype of an information system. So information search system is going to show us some documents, some web pages, because it thinks that these are relevant. And let's say we've got a training set with relevant and irrelevant results for each query. And again, 0 and 1 will depict relevant. And our predictions, so actually a prediction of an information system is going to be just the presence of a certain web page on SERP. actually this initial page with 10 results is called SERP, search engine results page. Okay, so 1 will be the presence of some instance in this SERP in the main page, and 0 are otherwise. What about these errors in these two cases? So actually these are also called type 1 and type 2 errors. There's analogy with statistics where you check some hypothesis and you either accept it or reject it. But I wouldn't call this type 1 and type 2 error. Everybody confuses these. Just call these false positives and false negative. This is going to be much more clear. Okay, in this third example, false positive is going to be some irrelevant page that is shown on the main page result, SERP. False negative is going to be some relevant result not shown there. Okay, in this case, we'll make a thinking face. So it's really not obvious which one is worse. So maybe you'll need some combination of these two metrics. Okay, we haven't discussed yet any metrics apart from accuracy, but in this case you'll need to introduce some weights for false positive and false negative. So it's not really very simple to answer which one is worse. Okay, so false positive is going to be interpreted as something irrelevant shown, but maybe one more interpretation. Actually, in search system, around 15% of all queries are really very, very simple. So about 15% of all queries, so it's really huge traffic. It's just FB for Facebook, maybe VK in Russian for vk.com, something like Gmail with misprints, or just GMA. Okay, so these are huge portion of 15% of all queries, around so. And so definitely for the query FB, there's the document or web page facebook.com, which is definitely most relevant here. And even for this query, we can say that any result is irrelevant if Facebook is not in the first position. And you see, false positive might be even interpreted here as Facebook not shown in the first position. So this is going to be a really bad mistake because it's a really huge traffic of around 15% of all queries. So if you take Google or Yandex or anything else, it will result in dozens of millions queries each day. Okay, but what about false negative in this sense? Let's say you've got some really very specific query. So let's say I'm near some park. Let's say, okay, my query is sorry. Let's say I'm in Amsterdam near some park, let's say Oster Park, and my query is finding some a pizza shop in Amsterdam near Oster Park. Actually, it means Eastern Park. Okay, this is going to be my specific query. So this one. So it's a really specific query, and suppose there are only 20 documents that are relevant at all for this query. And of course, a good search system is going to show it you on the main page, and false negative might be interpreted as not showing some specific query in the first place, or in the first page. So it's also going to be really very bad that your search system doesn't respond to specific queries. Okay, but it's really hard to tell which one is worse, and you see we need much more complicated metrics, and in With search system, there are even not hundreds, but thousands of different metrics. But in this simple case, we see that you can't say that either false positive is more important or false negative. Okay, so the first disadvantage of accuracy as a metric is that it accounts for false positives and false negatives equally. We'll quickly return again to false positives and false negatives. Just one more disadvantage of accuracy. So, in case of imbalanced dataset, maybe you are hunting for some really very rare event. Let's say that we predict whether a client is going to pay in our mobile application, and only 1% of people do actually pay. So we've got a binary classification, and there's only 1% of positive examples of +1s. Or I would say that the mean target value is around 0.99. In this case, you can have a very stupid baseline if you just predict that your clients are not going to pay ever. So just predicting each time that your object is negative, the instance is negative, is going to result in accuracy around average value of your target. Okay, sorry, and it's not 0.99. I would sneakily modify it. 1 minus average value of target is going to be 0.99, and average value of your target is going to be the percentage of positive instances, so only 1%. Okay, and so this is also going to be the expected accuracy if you just do nothing. You see? Okay, and now suppose you've got a real project and you need to build a prototype maybe in 2 weeks. And suppose you are a manager who doesn't understand all these disadvantages of accuracy, and you give your data scientist a task to build a simple prototype for a classification problem, maybe in 2 weeks. And your data scientist just analyzes the data set and sees that this is an imbalanced problem. And so actually for 2 weeks, this data scientist is going to do nothing, and then in the end he or she would claim accuracy of maybe 95%. And you as a manager hear some metric, 95%, and intuitively you might think that this is going to be a good value. So actually you ask yourself, is it good? But you see, without understanding this, the problem, this peculiarity of imbalanced dataset, you can't actually answer this question. So you need to compare it at least with this stupid baseline as always predicting negative values. So you need to compare it actually with this 1 minus your average target. And you see, the problem might be that your data science was doing nothing, and in the last day he built some really simple baseline and then reports this value of accuracy. So accuracy is actually not a very good metric in case of imbalanced dataset. So there are much better metrics for such problem. Accuracy is just not really sensitive when you are hunting for some really rare events. So let's go back to these confusion metrics. So for variance, for alternatives, true positive, true negative, false positive, and false negative. So we've seen in different applications either false positive was more important or false negative, or we actually can't say. So specifically for these two cases, these two alternatives, either false positive or false negative, we introduce these simple metrics like precision and recall. So precision is going to address the cases where you care of false positives. So the precision, to calculate precision, you take a look at all your positive classifications. So this is going to be the first row. You take a look at all cases where your algorithm claimed that this is going to be class 1. And then you just take the share of correct answers. So true positive divided over true positive plus false positive. And for recall, you keep track of this left column, all your positive examples just based on real labels. And then again, you calculate the share of correct answers. So it's going to be true positive divided by true positive plus false negative. And you see pretty clearly that one metric addresses false positives and another metric addresses false negatives. So in such applications where we hunt for something rare, maybe we need to keep track of recall. So like with cancer diagnosis, or the very same with clients churning, or something else. So maybe you are searching for some anomalies. In these cases, you are really interested in finding all rare objects, or maybe just all positive objects like people with cancer, because it's more important. So you are concerned with false negatives, and you just take a look at recall. Precision might be more important in our case, in case of spam, or in many other applications. But most probably you're not sure whether you need to focus on precision or recall, and you'll take a look at the average of these values, but not typical arithmetic average. One more metric is called F1 score. It's geometric average between precision and recall. So it's twice precision multiplied by recall and divided by their sum. So a motivation for introducing so actually a new metric is that unfortunately you can't have nice precision and nice recall at the same time. So a graph depicting the dependency between precision and recall will build these ones. You can ask what's actually variant here, why we have different values of precisions and different values of recall. We'll take a look at this, but typically this is the case. You've got either high precision or high recall, and you need to find some balance between precision and recall. And typically in applications where you've got imbalanced data set, instead of accuracy, you'll focus on F1 score as in some average between precision and recall. Okay, so actually one more generalization of these confusion metrics is when we have a multi-class problem. So let's say for a 3-class classification problem, we'll have pretty much the same confusion metrics, but we'll have true positives, actually true labels on the main diagonal, and then we'll have lots of types of mistakes. Okay, I'll draw these larger. So suppose we've got a 3-class classification problem. Let's say we're analyzing news and tell either if they are about Bitcoin or Litecoin, or maybe something general about cryptocurrencies. Okay, just nothing special, just an example of a multi-class classification problem. So Bitcoin, Litecoin, or just general about cryptocurrencies, and these are predictions, and these are real labels. Okay, on the main diagonal we'll have all these what we call true positives, but now we have, let's say, we can say true positive 1, true positive 2, and true positive 3. Okay, but what do we call by positive here? But okay, just three cases. And then we have all these variants where you confuse different classes. Typically, it's very important to analyze such matrices and to see all the instances where you confuse, let's say, a general paper maybe or news on cryptocurrencies with a Bitcoin. So it's very helpful to analyze all these sorts of mistakes, to see maybe actually to understand why your algorithm confuses this or that labels. Okay, so actually you've got some variants for precision and recall for such cases for multi-class classification problem, but there are two alternatives how you average these. So it's micro average or macro average. In micro averaging, you just calculate these precisions and recalls for each class. So actually we can take a look at BTC only. So we can calculate precision for BTC and recall for BTC. And then we can average all of these between three classes in separate for BTC, Litecoin, and crypto, and then average. Then this is called micro average. And macro average will be just to average all these values from the initial confusion matrix. In practice, as for me, I don't often distinguish between micro or micro averaging. I just pick the default one or just any one. It's more important to actually analyze these confusion matrices and to see how your model behaves. Analyzing confusion matrices will be really important if you're not sure about your labels. So I'll provide an example from my practice. It was the task of sentiment analysis for news on cryptocurrencies. So you've got articles describing various cryptocurrencies, and you've got analysts, some financial traders, actually some assessors reviewing them. So the idea is that you've got just some text, some news on cryptocurrency, and you need to classify it, let's say, in three classes based on sentiment. Either it's positive or negative or something neutral. Okay, so this is okay, positive, negative, and neutral. And it's about BTC. So either the article says something cool about Bitcoin, or something neutral, or something negative. Okay, the idea is that if you are a trader, you would like to, in the morning, to take coffee, and maybe previously it was a newspaper, but now most probably you'll go to search for some news about Bitcoin. But you've got thousands of them each day, and you can't analyze it yourself. So maybe if you have some such classifier, you can make a short summary what typically articles say about Bitcoin right now. Okay, the problem is that you need to assess it. So actually the first problem is that it's really hard to define whether some long article says something positive about Bitcoin or negative or neutral. So maybe the beginning is positive, in the middle you've got some negative information about Bitcoin, then overall you might think that it's neutral. So actually it's really hard to label this. And one more problem might be that your dataset will be scarce, so you're not going to have many labels if they are done by professionals. Okay, in this case it's really very important to analyze such simple thing as a confusion matrix. Just to explore these alternatives false positive and false negative. So if you've got true labels but you don't believe in them as a ground truth, it might be really funny to analyze such cases where your model might be correct but not your labels. So okay, I've got 3-class classification problem, but I draw a confusion matrix just for a binary classification. Okay, let's say we distinguish positives versus all others, then we'll have a confusion matrix just 2 by 2. So it's going to be really very helpful to take a look at false positives, all these cases, and just to take a look on them with your eyes. So just eyeballing, just read all these articles that are considered positive by your model and neutral or negative by your reviewers. You might find it that maybe your model is correct, not your labels. So with this procedure you can even question the quality of your labels. And it's really a very nice research topic, how actually to assess the quality of your labels. If you've got multiple reviewers, you can come with some techniques to actually average their results and to calculate some performance metrics for your human reviewers and whether to trust their labels or not. Okay, and the contrary case where with false negatives is also going to be interesting, where your model thinks that your prediction, so the prediction is not a positive for some article, but the true label given by assessor is positive. Okay, I started with a 3 by 3. Started with 3-class classification problem. So actually a confusion matrix will be a bit richer. So positive, neutral, negative, and the same for predictions. And you can analyze all these 9 cases, but maybe it's a bit more involved. Okay, let's go on. So we talked about binary classification or multi-class classification, but very often we'd like to analyze, to actually assess model quality in case where you predict some probabilities or just some scores for each class, but not labels. We discussed it somewhere here. Let me just remember. Why would we like to actually predict some value, some number treated as a score or maybe a predicted probability? Okay, in case of credit scoring, it's very, very important, but it's also very good in general just to have not zeros and ones output by your model, but also to have some level, some maybe degree of confidence of your model predictions. In this case, you can just rank your instances or maybe your clients based on model prediction, and you'll have some scoring. So it's really very important to assess your model quality in this case. And let's think about it. So actually, the most widespread metric for this case is ROC-AUC. ROC is receiver operating curve and some historical abbreviation. So it arises in signal processing domain. So actually, this ROC is not very important now for machine learning, just historical origination. And this AUC is area under curve. So this is the most prominent metric for the case where you predict some probabilities. Okay, so if you take a look at your training set, you'll have something like that. So you'll have real targets and your predictions. And we'd like to see that for positive examples, we have large values of predicted probability of class positive. So maybe 95 is going to be nice. Maybe for other positive example we'll have 0.7. Maybe we've done a mistake with another one, so maybe for some positive example we predicted only 0.2, only 2% that it's actually positive, and so on. And some predicted probabilities also for negative objects, maybe again for positives. A typical thing to do is to sort these values based on predicted probability. So let's just sort these guys in descending order. So I started to do this. Let's suppose that all these values below are much lower, maybe 10 to the power of -4. Okay, so this rating is actually called, okay, I don't know an official name for that, but we can call it a rating, or in credit scoring task it's a scorecard. And in lots of applications they just call it scoring. So if you've got clients, you've got some IDs, you have scoring for all of your clients, for actually all of instances in your dataset. And if it's not a training but a test set, you'll only have IDs for your clients and this predicted probability. Of course, you won't have targets anymore, and you assess somehow quality on training set, and then for the test set you'll only have this rating 0.8, 0.5, and so on. Okay, so if we trust our model, and we'll trust it when we calculate some metric, ROC, and see that it's nice. So if we trust our model, then we'll have this scoring for the test set, and it's nice. So we'll have some sorting from bad clients maybe to good ones. Okay, let's take a look at ROC, what it is and how it's calculated. So we'll have a toy example. Let's take the very same guys from this example. Okay, I'm not going to write all these names, but let's just have 6 objects. And so it's going to be a training set, so we'll have targets for these and we'll have predictions. And these are going to be, okay, I'm not copying this one, but maybe something similar. 07, 04, 015, and then 006, 002, and 001. Okay, so this is our rating or scoring. But our classification won't be ideal, so we'll have positive examples here, but then 0, then again 1, and again zeros. What we'd like to do is our predictions actually somehow to be correlated with targets. And with ROC, so area under receiver operating curve, you actually keep track of true positive rate. It's just the very same term as recall. So actually the metric is just the very same, but another name for recall, true positive rate. Another metric will be false positive rate. So these are positive rates, so either true or false positive rate. Again, drawing confusion metrics, true positive, true negative, false positive, false negative. So true positive rate is going to be the very same as recall, so we've seen a formula for that. True positive divided by true positive plus false negative. So we calculate recall based on truly positive examples in our dataset. And false positive rate is going to be a share of false positives for your truly negative examples. So it's calculated actually by the right column. False positive divided by false positive plus true negative. Okay, but how do we actually get all these variants based on the scoring? So in the end, you still need to make a discrete decision, like in this picture. You need to find some threshold to actually refuse to some clients and approve loans of other clients. And Rokauk is nice that it gets rid of this choice. So it's actually assessing true positive rate and false positive rates for all variants of for all values of your threshold. Okay, let's just pick some threshold like 0.13. And so all the values above this threshold are going to be classified as positives. So the prediction here will be +1, and all values below are going to be classified as negatives. In this case, we have let's calculate true positive rate and false positive rate in this case. Okay, you see, so for this value of threshold, you'll have predictions like that. So, okay, I'll draw it here. Prediction. I'll draw it magenta, so meaning that it corresponds to this threshold. So the prediction is going to be 1, 1, 1, 0, 0, 0. Okay, and so recall, true positive rate is going to be the proportion of all actually positive instances found by our model. So with this prediction, we correctly identify these two guys, but we fail to identify this one. So this is a positive object, but we missed it. And so in this case, true positive rate is going to be 2/3. What about false positive rate? This actually calculates the share of false positives. So let's calculate false positives. These are the cases when the real target is 0, but we predict 1. So we've got one such case. Here we predict 1, but the real label is 0. So we've got false positive rate of 1/3. Okay, and so if you vary your the value of this threshold, you'll have different values of true positive rate and false positive rate, and you'll have some curve. So if you depict true positive rate and false positive rate as a function of this threshold, you'll actually have some curve. Okay, let's actually build it. So let's start with a very primitive algorithm. So what if we just pick a threshold, let's call it tau, equal to 0. That means that we always predict class 1. So definitely our true positive rate will be 1. So because we find all positive examples. But at the same time, we'll make the largest possible number of mistakes. So it will correspond to 0.11 on this plot. So this tau equals to 0 will correspond to this point. On the contrary, if we set the threshold tau equaling 1, that will mean that we'll always predict 0. And of course, true positive rate will be 0, but at the same time, we won't make any false positives. So this point corresponds to tau equaling 1. Okay, and so if you vary this threshold, you'll get different values. Let's quickly skip through it. Okay, so for some threshold like 0.015, we'll have maximal true positive rate, and false positive rate will be 2/3. Okay, so here's 2/3. it will be this point. Then if we increase the threshold, maybe something like 0.4, false positive rate will decrease even further. Only one is left, only one false positive. So this is 1/3. Okay, for our example with dot 13, we had actually true positive rate decreased to 2/3. So this point will stand for a threshold 0.13 or any other between 0.06 and 0.15. Okay, if we increase threshold further, okay, so true positive rate will stay the same and false positive rate will decrease to 0. And we've got such a curve like this. Okay, so it depicts true positive rates and false positive rates for different values of thresholds. Well, okay. And now, finally, area under curve is actually this area under the curve that we just built. Of course, the ideal classification will be here. When false positive is 0, false positive rate is 0, and true positive rate is 1. So this point is ideal classification. And our model would like to, so if we build this area Rockout curve, sorry, so a perfect one will be just vertical here and horizontal here. And ideal area under curve will be equal to 1. But in our case, if we calculate, we've got this area under curve. Sorry, it's in our case, in not perfect case. So we have area under curve equaling to 8/9. What are reasonable values for area under curve? If you think about it, if your model just predicts a random value, it will correspond to this main horizontal line. So you'll be predicting positive numbers, and they will be equally true positives and false positives. And you'll have ROC-AUG equaling 0.5. So AUG, area under curve that equals 0.5, it's random classification. So there is no sense actually to take a look at values below 1/2. Okay, so area under curve is, I would say, by default metric for the case when you predict probabilities. The only problem is that it's actually a ranking problem, ranking metric. So suppose you just multiply all your predictions by some constant, you'll get not probabilities anymore, but just some scores. But your ranking will not differ in any sense, and you'll have the very same area under curve. And so, if you think about it, what makes this area under curve not ideal? Only the cases when you have a higher score for negative examples than for positives. So I'm drawing here just a piece of this scoring. If you have something like 0.8 prediction for a truly negative example and something smaller, let's say 0.4 for a positive one, so this is actually a mistake. So it's a misclassification. And ROC-AUG can even be interpreted as calculating the number of these misclassifications. And it's easily seen in this in our example. So how many incorrectly ranked pairs do we have in our case? We can actually calculate these ones. Okay, in our case we have 3 positive examples, 3 negative examples, and there are actually 9 pairs, how you can, actually 9 variants to combine, actually to compare one positive example with one negative, so just 3 by 3. And among all these comparisons, we can see that we've done an incorrect comparison, just one. Okay, if we take a look at the middle of this scoring card, we see that we've done a mistake. This is an incorrectly ranked pair. All other pairs are fine, just okay. We don't compare positives with positives, only we take a look only on pairs where one object is negative and the other one is positive. So we see only one misclassification, and 1 minus 1 misclassification of all possible 9 pairs, that gives us this rock oak. So actually rock oak can be interpreted as a share of correctly ranked pairs in our dataset. So it's actually a ranking metric, but it's very popular for classification when assessing probabilities. So closer to practice, it's nice to compare rock oak values for different algorithms. If you add feature, you can see that your rock oak increased. But I won't say that it's a nice metric just in practice for making decisions. It's not really very nicely interpretable. So this interpretation that it calculates the share of correctly classified pairs, so it actually doesn't help at all in real applications. And I would say it's not interpretable at all. Okay, sorry, I see that the part of this image you didn't see. Okay, so here with this, in this left corner, I just draw an incorrectly classified pair. So when your real label for negative example is higher than for positive. Okay, I think you got it from context. Okay, so rock oak is perfect for Kaggle. I think you now see the difference between Kaggle and real-world project. When in a Kaggle competition, you just have a metric chosen for you, and you need to optimize it by doing feature engineering, by training different models, ensembling their predictions. But your metric is typically fixed. And it turns out that in real projects, rock oak is not a perfect metric, and in the practical part, you'll see a clear example of that. So just the value of rock oak that equals, let's say, 0.95 doesn't provide you much information, only that the closer to 1, the better. Okay, lastly, I'll describe one more metric called lift, and it's much better interpretable. So it's some sort of a mixture between accuracy and rock curve, and sometimes in real problems it's much better to calculate lift. So we start from the very same scoring, actually just scoring, or maybe scoring table for your instances in training set. So you've got real labels and predictions, and your predictions are already sorted by predicted probability. Okay, so we've got this scoring, and actually we're interested in the top of this rating. Let's take a look at top K values. So suppose we're solving some task like predicting churn, and these labels and predictions will correspond to churn. Actually, I'm not interested in the whole data set. I think you'll be interested in top K positions and maybe K equals to 100 or something else. So just take a look at the top of this rating. So maybe in case of churn, we'll try to actually connect to these K clients, 100 clients or more, and try to propose them something, maybe some service or something else, just to prevent churn. And so these top guys in our rating are considered most prone to churn according to our model. And let's just focus on this part, ignoring just the rest of the rating. Let's just calculate the share of ones in this top rating. So it resembles Rock Oak just in a sense that we deal with this scoring rating, and it resembles accuracy in a sense that we'll just take a look at the proportion of positive objects in this top of the rating. To calculate lift, we'll first take the top of this rating. So lift all goes with this hyperparameter k. So to calculate it, we'll just calculate the share of ones in this rating. So the average value of y at these top k positions. And we'll divide it, so there are different variants, but we'll compare it somehow with the average value of y. We can sample the very same 100 objects from the whole dataset, or one more alternative is just to divide by the average value of target in the whole training set. So either the average, or you just sample random k instances from the whole training set. And so now lift becomes really interpretable. So it says, so when we calculate, let's say we calculated some number, let's say 4. In this case, lift will tell us that if we believe in our model predictions, we'll have on average 4 times more churned people than if we just randomly sample them. And if we'd like to spend some money and to propose some services to them, or maybe just make phone calls, this will tell us that we are 4 times more efficient. How do we set this hyperparameter k? So k, a popular thing to do is just to take 10%. But in business cases, k is settled by actually your goals. So in case of churn, you'll be phoning, you'll be calling these guys, and maybe k is actually how many people you can contact. Maybe only 100 per day. You just wouldn't like to spend more money on that. So in this case, you'll take k equaling 100. Okay, and lift turns out to be a really nice metric to use in practical cases. And in the next video, we'll take a look at such a case.